Okay, so in this video we're going to finish up talking about circular motion basics. Before we do that, I want you to try to answer this warm-up question on your own. So the question says a Ferris wheel rotates 3 times each minute. The passengers sit in seats that are 8 meters from the center of the wheel. And you're asked 3 different questions. What is the angular velocity of the wheel in degrees per minute and radians per second? What is the linear velocity of the passengers in the seats in meters per second? And then what distance does a person on the edge of the Ferris wheel travel through in 10 seconds? Okay, so see if you can answer those questions on your own. Okay, so we're first asked to find the angular velocity of the wheel in degrees per minute and radians per second. Remember, angular velocity, that is omega, and that is basically an indication of how fast an object is rotating, and we're asked to find it in 2 different units, degrees per minute and radians per second. Now we're actually given the angular velocity already, just not in the correct units, because we're told that it rotates 3 times each minute. In other words, every 1 minute that passes, it rotates 3 different times. And so 3 rotations, if you think in terms of degrees, each rotation is 360 degrees, and so if you do 3 times 360, we find that is 1080 degrees. And we're first asked to find the angular velocity of the wheel in degrees per minute. Well, it's this many degrees each minute. And so for the first question, you could just say omega equals 1080 degrees per minute, which is angular velocity, just not in SI units. But we also want to find it in radians per second. And remember that 1 full rotation or revolution in radians is 2 pi radians. Okay, radian is a unit of angle, and the conversion factor is such that 1 rotation or revolution is 2 pi radians. Okay, so 3 rotations each minute basically corresponds to 6 pi radians per minute. Or it might be easier to write this out as a unit conversion. Okay, so 3 rotations per minute. We want radians per second. We know in 1 rotation there's 2 pi radians. I'm going to write rad for radians. And we know that in 1 minute there's 60 seconds. Okay, so everything cancels except radians and seconds. And so we also find omega is in radians per second. If I do this correctly, I do 3 times 2 times pi, and then I divide that by 60. I get 0.31. Omega equals 0.31 radians per second. And so that is the answer to the first question. Now, the second question says, what is the linear velocity of the passengers in the seats in minutes per second? Now, in the last video, we talked about 3 different equations. We talked about the equation for arc length. We talked about the definition of angular velocity, which is basically defined as the rate at which your angular displacement changes over time. And then we wrote the equation that relates linear velocity to angular velocity. So remember, linear velocity is just the same old velocity we've seen all year. That's how fast you would move in a straight line in meters per second. Okay, well, as it relates to angular velocity, v is equal to r times omega, where r is the radius and omega is the angular velocity in radians per second. And so given the angular velocity in radians per second, which we just found, we can easily find the linear velocity of the passengers as long as we know the radius, which we know they're 8 meters from the center of the wheel, and so that would just be 8 times 0.31. And so if I type that into the calculator, 8 times 0.31, that's 2.48 meters per second, and I will round that to 2.5 meters per second just for sig figs. Now, what that means basically is that if one of the passengers was to fly off through the air, they would initially be traveling at 2.5 meters per second, okay, which hopefully wouldn't happen. But that's how fast they'd be moving in a straight line. Although I guess they would be in free fall, so it wouldn't really be in a straight line. But anyway, okay, so that's the answer to the second question. The third question says, what distance does the person on the edge of the Ferris wheel travel through in 10 seconds? Okay, well, this one relates to arc length, because if you imagine them going in a circle, the distance they travel in a circle has to do with arc length. And so here we have to use the arc length equation. I'm going to erase some of this just to clear some space. Okay, so for this last one, we need to use the arc length equation. That's going to be S equals R times theta, where R is the radius, which we know is 8 meters, and theta is the angular displacement in radians. But now we have to be careful to read the question carefully. Sorry, of course, that makes sense. Because we need to figure out what is the angular displacement in this situation. We're asked what distance does a person travel through in 10 seconds. Okay, so in other words, what is theta going to be? What is the angular displacement going to be in 10 seconds in radians? Well, this question now requires us to use the angular velocity and the definition of angular velocity. Remember, angular velocity is angular displacement over time. So if we know that the Ferris wheel is going 0.31 radians per second, and we multiply that by 10 seconds, that will give us theta. Okay, that's just coming from up here. That this is the definition of angular velocity. Okay, and plus it should make sense, like radians per second times seconds should give you radians. And so here, theta is equal to 3.1 radians. And now that we have theta, we can plug back in here. 8 times 3.1. I'm going to type that into my calculator. 8 times 3.1 is 24.8 meters. Okay, and so that's the answer to the third question. Okay, so hopefully after going through that example, you have slightly better understanding of how all these different concepts that we talked about in the last video are related to each other. Okay, so pause it there and make sure you understand this warm-up question, because this is like a good generic circular motion basics question. Okay, so let's move on. Okay, just a note, I want you to expect to have a quiz over circular motion basics. That's both this video and the first Edpuzzle video sometime next week, probably either on Wednesday or Thursday. Okay, so not the next class, but the class after that. Okay, so make sure you add that to your calendar. Okay, so I am going to do one more quick example, and then we will move on. The notes. Example 1.5 says a Ferris wheel takes 40 seconds to make one full revolution, and we're asked what is the angular velocity, so what is omega, in radians per second. Okay, so to answer this question, look at what you're given. You're given time, and you're given one full revolution. And so you got to think one full revolution is basically an angular displacement of 2 pi radians. And so given time and given the angular displacement, it makes sense to use the defining equation of angular velocity, which is angular displacement over time. And notice here I'm dropping the delta just kind of to save space, and also it doesn't really matter, but this is really technically a rate of change. And so if we know theta is 2 pi, and we know that time is 40 seconds, then all we have to do here is just divide. And a lot of people get confused in this unit because they can't figure out, like, how do I know which equation to use? Like, it asked me to find omega, but there's more than one equation. Okay, well, you have to look at what you're given. Okay, just like any physics problem. Here, we're given theta and we're given time, so it makes sense to use the equation that has those two variables. Okay, so if you calculate this correctly, you should get 0.16 radians per second. Okay, now the second question says a car tire rotates with an average angular velocity of 29 radians per second. In what time interval? So we're looking for time. will the tire rotate 3.5 times? Okay, so try to answer example 1.5 on your own. Okay, and this equation is basically, this problem is basically using the exact same equation, except now we're asked to find t. We're given omega is 29 radians per second, and if it rotates 3.5 times, remember each of those rotations is 2 pi radians. Okay, and so to find theta in radians, we have to take 3.5 rotations and multiply by 2 pi radians. And so that would give us 7 pi radians. And I'm not going to leave it in terms of pi. I'm actually going to just plug the value for pi into the calculator, the 3.1415, whatever value that's in the calculator. But if you rearrange this equation for t, you get 7 pi divided by 29. And when I type that into my calculator, which I'm doing right now, 7 pi divided by 29, I get 0.76 seconds. Okay, so just two really basic questions involving the definition of angular velocity. Okay, so pause there, make sure you understand how to do those problems. Okay, so now we're going to move on in this unit, and we're going to talk about a few new definitions. Okay, and the first one is what is called period. Okay, definitions are important, and I'm going to say that a lot this semester. Definitions are important, so please make sure you know and fully understand this definition. Okay, for an object moving in circular motion, the time to complete one full rotation or revolution is called the period. Okay, now you might think because it's period it would be like a capital P, but we actually use a capital T to represent period, not to be confused with the lowercase t. Lowercase t is time, any time, that's a variable time. The period is one specific time. Okay, specifically, the period is the time to complete one full rotation or revolution. In SI units, that would be measured in seconds, but sometimes period can be given in other units. Okay, so let me give you some examples. Okay, so here we're asked what is the period of revolution for the Earth spinning on its own axis. Okay, well, hopefully you know that the period of rotation for the Earth spinning on its axis is 24 hours. That's what we call one day. Okay, now, if we were doing calculations with this, we would need to convert that to seconds. Here we're just asked what the period of revolution is for the Earth, and it doesn't specify the units, so we're probably okay leaving it in hours from now. But if you were doing a calculation with it, if you wanted it in, to find some other quantity, you would probably have to convert that to seconds. Okay, but that's just to give you an example of period. Another example of period would be the period of the Earth revolving around the Sun. Okay, so what is the period of the Earth revolving around the Sun? Well, again, we're not really told what units we need the answer in. You could go really easy and just say that is 1 year by definition. Or you could say it's 365.25 days, or you convert that to hours or minutes or seconds, whatever you need. Usually it would specify it in the question. Again, if you don't know, the safest bet is always to convert it to SI units, which in this case would be seconds. Okay, so either it'll specify the units in the question, or if you don't know, if you're not sure, or if you're doing any other calculation, convert it to seconds. Okay, one more quick example of period. Example 3, it says a spinning object completes 3 revolutions in 24 seconds. What is the period of this object? This is a very easy question as long as you know the definition of period. Okay, definitions are important. We're told that it goes around 3 times, 3 revolutions, in 24 seconds. I'm writing hours, 24 seconds. By definition, the period of an object is the time it takes to complete 1 revolution. Okay, so if we want to get 1 revolution, we need to divide this by 3, which would give us 8, and so the period of this object would be 8 seconds. Okay, I'm not using any super secret equation or anything, that's just using the definition of period. Okay, so make sure you understand what period is. I'm going to go to the next slide. Something very related to period is the concept of frequency. Okay, and they're actually kind of inverses of each other. Again, definitions are important, so make sure you read the definition of frequency carefully. The frequency, f, that's a lowercase f, okay, lowercase f is a symbol for frequency, is defined as the number of revolutions, or I guess it could also be rotations, an object can make in 1 second. Okay, so period is the time it takes for an object to make 1 rotation or revolution. Frequency is the number of rotations or revolutions an object can make in 1 second. So it's kind of like the inverse of period. So for example, if an object can go around, let's say, let's go back to the last one, where it's 3 revolutions in 24 seconds. So the period was 8 seconds. That means it takes 8 seconds to go around 1 time. Okay, so how many times does it go around in 1 second? Well, that would be 1/8. Okay, and so frequency is the inverse of period, and you can calculate frequency using the equation 1 over t, where of course capital T is a symbol for period. The symbol, or not the symbol, the unit for frequency is hertz. It's named after the physicist who discovered radio waves, and it's given the abbreviation Hz. Okay, so if I had a frequency of, let's say, 2 hertz, I would write it like that. Okay, so frequency is measured in hertz. And of course, that would correspond to a period of 1 over 2, which would be 0.5 seconds. Okay, so in other words, 2 hertz means it goes around 2 times every second. That means it takes half a second to go around once. Okay, so frequency and period are related to each other like that. Okay, and just do a really basic example. Broken CD player spins with a frequency of 120 hertz. Calculate the period of revolution for the CD player. If frequency is 1 over the period, you can just rearrange this equation using algebra and find that period is also equal to 1 divided by frequency. Here we're given the frequency is 120 hertz, so that's just 1 over 120. Okay, don't leave your answer as a fraction, please write it as a decimal. So you should actually do 1 divided by 120 in your calculator, and you should get 0.0083 seconds is the period. Okay, so just a really basic example with period and frequency. Alright, so moving on, I want to introduce just a couple more equations to finish out this part of the unit. The first equation I want you to see is the equation that relates linear velocity to period. Okay, so just to back up for a second, the whole reason why we switched from talking about like angular velocity and linear velocity and then we randomly started talking about period is because period is something that is easy to measure. It's not easy to look at something and know how fast it's moving, but it is easy to measure the period of something because you can just watch it and see how long it takes to go around 1 time. Okay, and so I'm going to derive a simple equation for you. Okay, so imagine you have an object moving in circular motion. So let's say I have a ball on a string and it's moving in a circle and the radius is r. Okay, I'm going to do my best to draw a circle here. Okay, so think for a second. What distance does this ball travel? If it's going around in a circle, what distance does this ball travel in 1 revolution? Okay, well, hopefully you know that the distance traveled in 1 revolution is just the circumference, and so that would be 2 pi times the radius. Okay, now how long does that take? Well, 1 revolution like the time for one revolution by definition, this is distance. The time for one revolution by definition is the period. Right? That's the definition of period. It's the time it takes for one revolution. Okay, so we can derive an equation for linear velocity, v, just using our good old distance over time equation. Okay, just basic physics. Okay, how far does it travel divided by the time? Okay, how far does it travel in one revolution? 2 times pi times the radius. Divided by what is the time it takes to go that far? 1 period. Okay, and so here is an equation that allows us to calculate linear velocity given the period and given the radius of the circle. Okay, so this is the next equation you should have in your notes. Okay, basic distance over time. Now I want to derive one more equation using the same kind of principle. Let's go back a second to the definition of angular velocity. Angular velocity is angular displacement over time, right? The rate at which angular displacement changes over time. That's how angular velocity is defined. Okay, so let's use a similar line of thinking. Let's say, hypothetically speaking, what if that t was the period? Okay, what angular displacement does an object travel through if the time is equal to 1 period? Think about that for a minute. Okay, in 1 period, by definition, an object travels through an angular displacement of 2 pi radians, right? Because 1 period, that time is 1 revolution or 1 rotation, and that's 2 pi radians. Okay, so just again using this equation, if t is equal to 1 period, then by definition theta must be 2 pi radians. Okay, and this is the next equation that you should have in your notes. Okay, and so notice that by measuring the period, you don't need any other variables, just the period by itself can give you the angular velocity. Okay, if you also know the radius of the circle, you can also calculate the linear velocity. Notice, by the way, if you compare these two equations, if you take omega, which is 2 pi over t, and you multiply by r, then you get the same equation that you see there on the left, which makes sense because this has already been one of our previous equations. Okay, so that should make sense. Okay, the one at the top, that's not a new equation, that was an equation from the last video. Okay, so here we have 2 new equations, and so basically what I'm saying is that because period is something that's easy to measure, if we can measure the period of an object in circular motion, we can find its angular velocity, and then we can possibly find some other things as well. Okay, so pause it there and make sure you have those equations added to your notes. And let's finish up this video with some examples. Okay, let's see. I already talked about that equation. Example 1. Actually, I'm going to skip that example. I want to take a look at example 2. Here we basically see all the equations I just talked about. Okay, so example 2 says a 3 kilogram stone on a string with length 2 meters is spun in a horizontal circle. It completes 1 full revolution every 4 seconds. Okay, and then we're asked some questions. First question says, what is the period of the stone? Easiest question in the book as long as you know the definition of period. Okay, we're told there's 1 revolution every 4 seconds. Well, period by definition is the time for 1 revolution. So that means the period is 4 seconds. The second question asks us to find the frequency, and of course frequency is 1 over the period. So that would be 1 over 4, which we know is 0.25. So that would be 0.25 hertz. Okay, now we're asked about the angular velocity of the stone. Okay, using the equation we just derived a second ago, we know that angular velocity is 2 pi divided by the period. By the way, somebody's going to ask, what's the difference between this equation here and this equation here? Okay, actually, let me rewrite this, two separate equations, okay, so that you understand the difference between the two. Okay, so this is the definition of angular velocity. This equation works for any theta and for any t. This equation specifically works when you are given the period, okay, which is a specific value. Lowercase t is a variable time. That can be any time that you choose. Uppercase t is one specific time. That's the period of revolution or rotation. Okay, so anyway, we are given the period already, and so it makes sense to use this equation to find omega. That would be 2 pi divided by 4. And so in my calculator, I'm going to do 2 times pi divided by 4, and that's going to be 1.57 radians per second. And then the last question asks us, what is the linear velocity of the stone? Okay, at this point, either we could use this equation, or we can use this equation because we already have the radius and we have omega, because we're told that the string is 2 meters long, which means the radius is 2 meters long. And I think this one might be easier to use. Okay, either way you get the same answer. Okay, so V equals R times omega. R is 2, omega is 1.57, and so we get 3.14 meters per second, which coincidentally is equal to pi. Okay, so that is example 2. Hopefully you're starting to see how all of these different pieces fit together. And we're just going to look at one more quick example, and then we will be done with this whole section of this unit. Okay, so pause there if you need to look at that some more. Okay, last question. Example 3. Okay, try to answer this question on your own. Okay, so example 3, a hard drive disk spins with a frequency of 120 hertz. That's about 7,200 RPM. If you ever go to buy a hard drive, by the way, a lot of the time it says the RPM on the hard drive. It might be like 5,400 or it might be 7,200, and you can easily calculate that into hertz if you want. Okay, so there is a frequency, and we're first asked to find the period. Period is 1 divided by frequency, and so that's an easy calculation to do. 1 divided by 120. Okay, so in my calculator I do 1 divided by 120. That's 0.0083 seconds. That's actually the period we had a few examples back. The second question asks us to find the angular velocity of the hard drive. Again, given the period, it makes sense to use the equation that has period in it. So that would be 2 pi divided by 0.0083. And so I get an angular velocity when I do that in the calculator, 2 pi divided by 0.0083. I get 757 radians per second, which is quite fast, of course. And then the last question says, if the reading head of the drive is located 3 centimeters from the rotation axis, calculate the linear speed of a point on the disk below the reading head. A reading head, basically, if you look at this picture, this is the part that actually reads the disk. So the farther out you get from the center of the disk, the faster the linear velocity is of the disk. And that's just because of this equation here, V equals R times omega. Okay, so every point on the disk has the same omega, okay, because every point on the disk takes the same amount of time to go all the way around one time. But the farther away you get from the center, the faster the linear velocity is. Okay, and so at the edge of the disk, it's 3 centimeters from the center. We're asked to find the linear speed of a point on the disk below the reading head. That is a simple calculation as long as you remember that 3 centimeters needs to be converted to meters. And so that would be dividing by 100. That would be 0.03 meters. And so for that last one, we would do 0.03 meters multiplied by omega, which is 757 radians per second. And I get 22.7 meters per second for my final answer. Okay, I will also tell you in passing, if you do buy a hard drive, it's better to buy one with a higher RPM. The faster the RPM is, that means the frequency is higher. That means the disk can spin faster. That means it can read information faster, which means basically, stuff on your computer can load faster, which is nice, especially if you do like a lot of game playing. That means your games can boot up faster because the disk is spinning faster, so that means the information can be read at a faster rate because omega is higher. Okay, so that is it for this third of the unit. In the next video, we'll start talking more about centripetal force and centripetal acceleration. As always, please let me know if you have any questions, and I'll see you guys in the next video.